Okay, so we'll start with some questions from the homework. On your assignment, question number 13, I'm just going to borrow your page for a second to go over this question. Question number 13 says that the probability of C happening is 0.44. The probability of C intersect D is 0.21. The probability of C union D is 0.83. Find the probability of the complement of D. You can do this with equations. I'm a visual learner, so I like to draw it out visually. Union means the whole Venn diagram. Okay, everything is 83%. Intersect means the place where they overlap. So I know right from the beginning that I have 21% in the overlapping area. The probability of C represents the whole left circle. So I already know that I have 21% in the middle. So 21 plus 23 is 44. So the whole C circle is equal to 44. Does that make sense? Great. So now I know that both circles altogether is 83. So far I've got 44. So how much more do I need to get up to 83? Almost 40 more, 39 more. And because I've got 83 inside the circles, that means I must have 17% outside, so that the total is 1. Okay, the probability of not D is the probability of everything that's not in circle D. So that is 17 and 23, which is 40%. Okay, so I love to solve those problems just using a picture. It helps me to understand what's really going on with the problem instead of all the crazy equations. Are there any other questions? Yes? Taking a look at question 14. So, in this one you're given probabilities as a function of x. So we know that not G is 3x, H is 4x, the intersection is 1/4, and the union is 9x. This one might be a little bit harder to do with the diagram, but again, because I'm a visual learner, I like to do it that way. So remember, the intersection means the place where they overlap. The union means everywhere. H will be the right circle, and G, not G means everything not in the left circle. So drawing a Venn diagram, I have 1/4 or 25% in the middle. Yeah, this is not so nice. This is much better with equations. I can say that the probability of the union is the left side plus the right side minus the middle. Okay. If not g is 3x, that means that g is the opposite, 1 minus 3x. Because g and not g have to add up to 1. So g is going to be 1 minus 3x. Exactly the opposite of not g. H is 4x, and the intersection is 1/4. And all that is equal to 9x. Using that, you can solve for x. Okay, so I had to use the fact that p of g and p of the opposite of g is 100%. That's how I can find out what p of g is. Okay, I won't go through all those steps for you. You can do that on your own. Are there any other questions? So I'll be collecting this worksheet at the end of class today. So you can turn to the first page. This is the last new topic in probability. And it's mostly tree diagrams. So we're going to start with a simple example. If you have the numbers from 1 to 10, and we take a number at random, we're just going to make a diagram here where E represents all the even numbers, S is all the square numbers, and E complement, which can also be written as this, is the ones that are not even. So on the left side, we'll have all the even numbers, 2, 4, 6, 8, and 10. But in the middle, we'll put the one that's a perfect square. So all the perfect squares will go in the S bubble. On the right side, we'll put all the odd numbers, 1, 3, 5, 7, 9. But the perfect squares we'll put into the middle. So 1 is a perfect square, 9 is a perfect square. Okay, so the first question is, what does PS line E even mean? And from last class, we learned about this as a conditional probability. When you see that bar, it means that you're given information. This is a probability of S given E. Okay, in ordinary English, that means, what's the probability of getting a perfect square if we already know we got an even number? So it's like I put the numbers 1 to 10 in a hat, and I picked out one of them, and I looked at it secretly, and I told you, I know it's even. And what's the chance that this number is perfect square? It's 1 in 5. Yeah, there's one perfect square out of the 5 possibilities of even numbers. So that conditional probability means we're only looking at the even side of the box. So the chance is 1 in 5. One perfect square out of 5 even numbers. And quite often, the easiest way to solve a conditional probability problem is by making a tree. So let's imagine that we've got a deck of cards, and we're going to shuffle them and take out 2 cards. What's the chance that the second card is black? And again, this is a dependent probability because we're not replacing the cards. So we can model this with a tree. I'll make my tree sideways this time. And to make a tree, usually you're going to talk about the first event as being the first branch of the tree. And then the second event, whatever happens next, will be the second branches of the tree. So we got two possibilities for the red card, or for the first card. It's either red or black. If the first card's red, we've got two possibilities for the second card. The second card could be red or black, and the first card could be black, and then the second card could be red or black. And on your tree, we're going to write down the probabilities associated with those events. So for your first draw, the chance that you get a red card is a half, and the chance that you get a black card is a half. So again, I'm taking my deck of cards, taking out one card, not putting it back. What's the chance that the next card is a red card? There's only 51 cards left for all of these ones. And why is it 25? That's right. We assume we took out one of the red cards. So we're already down from the 26 that we started with. So that means there's only 25 red cards left. But how many black cards? 26. So if the first card was red, then there'd still be 26 black cards. So we'd have a 26 out of 51 chance of getting a second card that's black.
How do we know this first?
We're following the path on the tree. Yeah, so we're making that assumption. So on the second part, we're assuming that the first card was black. So now we only have 51 cards left. How many of those ones are red? 26. Very good. And that means there's only 25 black cards. So there's two ways that we could get the second card being a black card. And that's if we follow this branch of the tree or this branch of the tree. Now when you're following a tree, to follow the probability that the first card's red and the second one's black, those two events are independent. Or not independent, but we can use the formula that we learned last time and just multiply the branches on the tree, and that gives us the total probability for this branch. And the probability for this branch comes from the probability that the first one's black and the probability that the second one's black, given that the first one was black. So we have 13 out of 51. And 25 out of 102. And how can we find the total probability? Just add them up. Yeah, they're two separate possibilities. So if we added all of these branches up, we'd get 100%, because that represents all the possibilities. So we'll do 26 out of 102 plus 25 out of 102. This is kind of interesting. You get 51 out of 102. And if you simplify that fraction, it's a 50-50 chance. Yeah, but sometimes one arm is weighed more than another arm. Sometimes one arm will be really, really likely and another one will be totally unlikely. What this is saying is that if I take out a card and don't replace it, if you don't know what that card is, then it's almost like I didn't pull that card at all. So taking a second card is the same probability as if I hadn't put aside this first card. If you don't know what it is, it's just like it's still in the deck. So really it's a 50-50 chance of getting a black card on the second try. Now the next part is a little bit more complicated as a diagram. This is not going to be too important for you, but it's for interest's sake. If you want to know the total probability of something happening, if it's a conditional situation, then what you can do is you can just find out the chance of A and B happening, which is this part here, and add that to the chance of B happening and not A happening. And that's what's described by this equation down here. But mostly we're going to solve these problems using a tree. So you don't have this formula on your IB exam because most conditional probability questions will just solve it using a tree. So this part here represents the red highlighted, and this part here represents the black highlighted part. And that just comes from the formula that we learned last class. Okay, but that's not going to be vital for you, especially as IB students. And same thing with Bayes' law. It's not one of the ones on your formula sheet, but we're going to be using it indirectly when we're doing tree problems. So I've chosen 3 really typical tree problems. And the first one is about a vehicle rental company. And with this rental company, you've got 2 dealerships. 75% of the cars are from dealership A, 25% from dealership B. During the first year, 16% of the cars purchased from A require major repairs, whereas only 20% of the vehicles from dealership B require major repairs. So we choose a car at random. What's the chance that they will require major repairs during the first year? So again, we'll model this using a tree, and the first decision is the first branch of the tree, and the second outcome is the second branch of the tree. So the first thing you have to decide are you going to go to dealership A or dealership B? And the second thing that you figure out is, does your car need repairs or does it not need repairs? Repaired or it does not need repairs. So the chance of getting a car from A is 75%, because 75% of the cars come from A, which means that the rest must come from B. When you're making a tree, 2 branches will always add up to 1. Okay? It should always add up to 100%. Now let's see, if the car came from A, the chance that it needs repairs is 16%. So then what's the chance that it doesn't need repairs? 84. Okay, those 2 branches, whenever a tree branches up into 2 parts, those 2 always add up to 1. From car dealership B, 20% of the cars need repairs. So that means that the rest of the cars, 80%, don't need repairs. So now we're going to find out what's the chance that a car will require major repairs. So we want to know all the ways that we're going to get repairs. We can get repairs by getting a car from A, or we can get repairs by getting a car from B. So that would be 75% times 16, or comes from B and needs repairs. So typically, especially in a tree problem with probabilities, if you're saying to yourself the word and, you're multiplying. If you're saying to yourself the word or, you're adding. So we want to know what's the chance that it comes from A and needs repairs, or the chance that it comes from B and needs repairs. So let's just take out a calculator and figure that out. If the answer is more than 1, you've made a serious mistake. So there's a 17% chance. that you're going to get a car that needs repairs? Yes. It's equally good both ways. I like working in percents just because it kind of makes everyday life sense. Now's where it gets difficult. Suppose that a car requires major repairs. This information is given. It's almost like the question that we started with. Suppose you already know that the number is an even number. Okay? If you already know the car needs repairs, what's the chance that the car came from dealership B? So you're given that you're only allowed to look at the yellow part of the tree. You're only allowed to consider all the possibilities where you need repairs. You want to know, what's the chance that it came from B? So the car that needs repairs that comes from B is this branch here. Okay, so for your total space, you're only allowed to look at all the 17%. We want to know out of the 17%, I want to highlight that yellow. 17% represents the total of all the cars that need repairs. So out of those 17%, what percentage came from B? So to find the green one, we're going to do 0.25 times 0.2. So we want to know what's the green if we're only considering the total yellow space. So what is 0.25 times 0.2 out of the 17%? And you get 29.4%. So if your car needs repairs, the chances it came from B is 29%. It's pretty low because most of the cars come from A. Even though there's a higher breakdown rate at B, there's so few cars at B that really there's not a very high chance that you would get a car from B in the first place. If they had the same breakdown rate at both places, then this answer would be 25%. Okay, but because B has a slightly higher breakdown rate, the answer is slightly higher than 25%. Okay, I'm going to give you a moment just to try this question on your own. So you're going to want to make it a tree. This is about a survey. 60% are women. The rest are men. And women accurately report their height 10% of the time, whereas men accurately report their height only 5% of the time. So what's the chance that a person has reported their height accurately? And then the second question is just like part B from the previous one. There's a conditional part to it. So just take 3 minutes or so to form the tree and try to solve this question. And this is pretty much your hardest probability problem right here. Congratulations. So the chance of getting a woman is 60. 40% are men. Women respond 10% of the time right, whereas inaccurate is 90%. Men are 5%, so that means that non-accurate is 95%. So the chance that they report their height accurately is just following the two branches where you could get accurate results. In part B, there was a little bit of a trick with the wording. If you multiply that on your calculator, you get 0.08, which is 8%. Now, I tricked you with the second question because of this word here. So, you were given that they did not report their height accurately. So that means you're not looking at 8% as a total. You're looking at the opposite. You're looking at 92%. That's just doing 1 minus 0.08. Because if this is accurate, then not accurate is exactly the opposite. You could also check that by actually multiplying both these branches together. You would also get 92. Okay, and we want to know, out of all the not accurate people, which ones are not accurate and male? These ones. So which ones are not accurate and male? So not accurate and male is 38%. Out of 92 is a total of 41.3%. That's on the video. That's gonna be on YouTube. The last question is the hardest type of probability problem. Well, it's the same genre, just with a little bit of twist and understanding. And the reason why this one's a little bit harder is because of the understanding of the wording in the question and what happens first. So you want the first thing on your tree to be the thing that actually happens first. So in this question, you've got a medical test that's 97% accurate. Suppose that 0.25% of the population has the disease. What's the probability that a person who tests positive has the disease? So the question is, what do you do first? Do you take the test first, or do you have the disease first? Yeah, you either have the disease or you don't. That's the first thing that happens. Are you diseased or not? So just because they say something about the test as the first sentence of the question doesn't mean that you should put that as the first branch of your tree. So the first thing is, do you have the disease or not? The second thing is, do you test positive or negative? So if 0.25% of the population has the disease, how many don't have the disease? 99.75. It's This is not 25%. That would be a really sick country. Yeah. So actually we have 0.0025 with the disease. Most people do not have this disease. And now is where it kind of messes with your mind as well. Where is the accurate? If you have the disease, should you test positive or negative? You should test positive. That means if it's accurate, you're going to be testing positive. If you don't have the disease, then you should be testing negative. So if you test negative, that one is accurate. So that means that the negative test for diseased people would be 3%. The positive test for non-diseased people would be 3%. So, who tests positive is the given part. So we're given that we want to only look at all the people that test positive. And then if they test positive, what's the chance that they also have the disease? So that would be the diseased people that test positive. So we want to know, out of all the yellow people, how many green people are there? So there's actually quite a large percentage of people that test positive even though they're not sick. That happened to my dad when he was giving blood. He tested positive for AIDS. He wasn't allowed to give blood again, even though he didn't have AIDS. Sometimes the test goes wrong. So I'll do the denominator first. So there's actually 3% of the population almost who test positive even though they don't have the disease. So did you get 7.5%? Make sure you have your brackets around the denominator. Rounds off to about 7.5%. So 7.5% of the population has the disease, or if they test positive, has the disease. That's a chance that if they do test positive, they have the disease. So that means that there's like 92.5% of people that test positive that don't actually have the disease at all. Yeah, it's a problem with the test. So unfortunately that happens. Yeah, it's 97% accurate. But that means that it made so many mistakes that actually it told a lot of people that they were sick, even though they weren't. Kind of like it did with my dad with his blood test.
But this is just like a chance for not actually.
This is similar to some of the actual results that you get from a medical experiment.